So thank you very much for coming to my talk, and thank you so much to the organizers for letting me talk about my work here. I'm going to be explaining something that I briefly mentioned in my 1-minute gong show in September, so it is cool to be back at the end of the program and explain these results. My goal was for the paper to be out this week so that I could tell you the numbers so that you can go and check it, but we had so many seminars that was impossible. But I told myself it will be out next week. Okay, so I will mention some results from my previous paper with Chang-Ha Choi, who is a postdoc at Perimeter, and Jaume Gomis, who is my supervisor. But mostly I will be talking about this upcoming work that, as I said, is not there yet. But I also wanted to acknowledge that the idea of this project was given to me by my supervisor. And yes, I'm very grateful for that. And this is going to be the outlook for the talk. I will start with I prepared a very long pedagogical motivation because I thought I was supposed to talk to a very diverse audience, but I think everyone knows more holography than me here. So maybe I will skip some of the slides and we can leave earlier. And then I will motivate my problem. After that, I'm going to introduce who are the main characters in my calculation, and these are these half-BPS surface operators of n equals 4 super young mills. I'm going to tell you about what is their holographic dual, and then I will explain how to compute the 10D on-cell action on these solutions, and what is this 9-dimensional counter term, and how it solves my problems in this very specific case. And then I will mention some general ideas of other calculations to do and yes, future work. And yes, please interrupt me and ask me any questions. So I will start by introducing the holographic duality in this very specific setting. I will always be talking about n equals 4 super young mills, this 4-dimensional theory that I think all of you know, and its dual type 2B string theory in ADS 5 times S5. I will not mention string theory. I'm going to always be talking about the low energy supergravity limit. So this is going to be the limit in which the string length is very small. So that's why we have supergravity, and also there are no quantum corrections. And we see that this strong weak duality means that the results that I get in this limit are going to correspond to strongly coupled results in the quantum field theory side and strongly coupled results in the planar limit. So in particular, the correlators or the observables from the quantum field theory that I want to map to this other side are going to be correlators that we have been able to compute for all values of the coupling constant, so that I can really find this exact matching in the holographic map. And so my talk is mostly about boundary terms and boundary conditions. So I took these 2 lines from Maldacena's paper, in which he said that he proposes this conjecture, but that he didn't know what are the appropriate boundary conditions for the fields in the gravity theory. And you know that right after that paper, all these other people figured out what are the right boundary conditions. And what we know is that the holographic duality gives us a prescription to compute correlation functions in the conformal field theory from the on-cell gravity axiom. So yes, and I wrote here the string theory partition function, whatever this means, but I will not discuss that at all. So in these papers, they understood exactly what are the correct boundary conditions for the fields in ADS, such that when you evaluate the gravity action on the solution to the equation of motion with this boundary condition, you can compute correlation functions. And you compute this correlation function of local operators by taking derivatives with respect to these sources. So one ingredient of the holographic correspondence is this map between operators in the conformal field theory and fields in the gravity theory, and then this recipe for the correlation functions. Okay. And in all these last 25 years, many people have been working in developing this dictionary. And the idea is that to any object that I can have in n equals 4 super Young mills, and these are local operators, but also non-local operators, defects, and all the operators that we have been discussing these days, I need to be able to assign something that happens in the gravity side, and I don't want to only map the operators, but also map the observables that I use to learn about these operators. So for the case of the local operators, it was very well understood how to do this perturbatively in the bulk, and also for other non-local operators. Okay. And something that was found very early on is that when you just take the gravity action and you evaluate it on cell, this has divergences. And this is not surprising because it also happens in the quantum field theory side. And people in all these papers and other papers understood how to regularize these divergences in order to get physical quantities that you can map to the quantum field theory side. And this systematic procedure called holographic renormalization gives you an instruction to do this. It given some gravity theory in anti-de Sitter spacetime or asymptotically anti-de Sitter spacetime, perhaps with some matter, you learn what are the boundary terms that you need to add to this action so that the divergences are cancelled, and also you get the correct finite term to compare or to predict Gates theory results. And here it was also there was also work in understanding what is the physical meaning of this procedure. So the same way as we understand renormalization in quantum field theory as something that is physical and that we don't do just because we don't like infinities, it is also understood in ADS-CFT how these boundary terms are related to the boundary conditions of the fields in ADS. Okay. But I started saying that, that we have a duality between this 4-dimensional theory and a 10-dimensional theory. But suddenly I went from the 10-dimensional theory to the 5-dimensional theory, and I didn't say anything about it. And that is what my project is on. So the usual story that now is very well developed of CFT on the boundary of this spacetime can be understood from the higher dimensional point of view after, as something that you find after you do Kaluza-Klein reduction and you do consistent truncation. And I want to explain what this is. So you do Kaluza-Klein reduction on this 5-sphere, and so what we will get is that the coefficients from these SO6 spherical harmonics are going to be the fields of my lower dimensional axiom, the same thing that we know for the hydrogen atom, and I do spherical harmonics in the sphere. And but now the question is, when I do Kaluza-Klein reduction, I have this infinite tower of Kaluza-Klein modes, and I don't want to call a theory of infinite fields a theory. What I want is just a theory of a finite number of fields. So people. So many people worked in doing this step of removing these infinite towers of fields and just keeping, for example, in this case, the massless sector that gives you some Gates supergravity on ADS5. And then after we do this is when we can use all the tools that the people that worked in holographic renormalization.
Sorry, I'm confused because I thought all of these towers of KK modes do correspond to operators. as of 6.
Yes, that's true. That's true.
So if you throw out these fields, don't you get a different theory? Maybe still to some other field.
Yes, I think that's exactly what I'm trying to convey, that we cannot just throw away these fields, but the way to compute correlation functions for these higher harmonics is not using the usual rules of holographic renormalization, but doing something a little bit more subtle. Does that make sense?
Well, no, more subtle, but
I wanted to explain it.
you can explain it in the subsequent slides.
Yes. Yes, but that is exactly the point I'm trying to make, that
you are cutting out all the Kaluza-Klein modes, and therefore you do not have the correspondence of, for instance, scalar mastic operators.
Yes, I will put them back. What I'm trying to say is that now, so the work in ADS-CFT, there has been also a lot of work just from this lower dimensional perspective, and like all the bottom up holography, in which I don't care about the higher Kaluza-Klein modes, and I can do physics just with this, but I'm trying to say that, I mean, there are many examples of that this is not all the physics, but I'm going to discuss a specific example that hasn't been studied yet. But yes, I think I will mention that later. Okay, and so it's going to be important to define what does it mean for this truncation to be consistent. It is, so we are starting with some 10-dimensional theory, then we are getting some 5-dimensional theory after doing Kaluza-Klein reduction, and we are going to say that the truncation is consistent if any solution to the 5-dimensional equation of motion can be uplifted to a solution of the 10-dimensional equation of motion.
Modes in this truncated set you're talking about, it won't excite the other modes?
Yes, exactly. And what I'm going to be discussing is there are some specific solutions, not ADS5 x S5, but other solutions where you cannot do that. You cannot just turn on some modes and not turn on any of the other modes. Or maybe I can stop here. Any other question? Okay. Okay, yes, so I guess this is what I wanted to say. Not every solution of 10-dimensional or 11-dimensional supergravity is going to belong to a consistent truncation. But we, or the people that believe in holography, thinks that holography is not only for consistent, or holography shouldn't be only for consistent truncations, but in general, it should work for any solution of the type 2B supergravity theory that is asymptotically ADS5 x S5, but it doesn't have to be exactly ADS5 x S5. So maybe I cannot expand in spherical harmonics and just keep a finite number of them. And yes, I will explain specifically. It will not be all blah, blah, blah. I will write down the equation. And so again, this is not something that is very new. People have been worrying about this problem and trying to solve it several times. I took specifically related to holographic renormalization, because as I said, the recipe for boundary terms is a recipe for boundary terms in the boundary of ADS. So not in the boundary of the higher dimensional ADS times compact manifold. And in this paper by Skenderis and Taylor, where they compute those kind of correlations that you were mentioning, it's a paper called Kaluza-Klein holography, and they ask this question of, given some 10-dimensional solution that is asymptotically ADS times compact manifold, how can we compute expectation values of some operators that are gauge invariant and that I know how to compute in the dual field theory. And I repeat the same question in this other way. That is, what do we do with all the solutions that we know, because we know many of these, that I cannot understand them as coming from some uplift. And so I wasn't going to explain, but I can do it. The way that they solve this problem for the 1-point functions, so what they ask is, yes, how to do this in something that is asymptotically ADS5 crosses 5. And what they do is take your fields and you want to expand in spherical harmonics. And what you are going to do is to keep, to formally keep all the spherical harmonics and plug it into the action and find a 5-dimensional action with a five-dimensional action that is perturbative in the number of operators. And you will see that for computing a specific correlation function of an operator that is of order, let's say, 2, you are only going to need to keep up to 2 operators in the 5D on-cell action, because this correlation function is computed as, okay, I wanted to write something like this, as some derivatives of the on-cell action. So since I want to compute these derivatives, I don't need to keep the whole tower of modes, but I can keep just a finite number of them. But these modes are going to mix, and that is going to be very important. So for example, some operator of conformal dimension 4 is going to mix with some mode, yes, 2 modes of conformal dimension 2. Okay, but this only works for correlation functions, and this is a very complicated procedure. They wrote the formulas for delta up to 4, and they did many checks that were important, but yes, it's complicated and it works for correlation functions. But you see that it only works because of these derivatives. So if I want to just compute the on-cell action, I cannot use it, because because I'm not going to take the derivatives and then evaluate to 0. I just want the full on-cell action. This procedure doesn't work. And or maybe is there, yes, I wrote this very schematically, is that I wasn't going to explain like this? Oh no. Oh, thank you. Oh no. Okay. Is it there? Okay. Oof. Every time I get a little bit more nervous. So, okay. So this procedure that they did works for these correlation functions, and I will give you an example of something that they computed that is like yes, it's like really hard and really impressive. And but I'm going to talk about this other case in which what I want to compute is the on-cell action, so I cannot use their procedure. And the specific example where this problem is going to be manifest is one of these so-called bubbling geometries. It's a solution of the higher dimensional equations of motion that cannot be truncated. Okay, so this is just to motivate what are these bubbling geometries. As I was saying in the beginning, in holography, we want to map any object of the CFT to an object of the gravity theory. And for the and there is a relation. This is for scalar fields of between the mass of the object in the gravity theory and the conformal dimension of the operator on the CFT. And then we can think from our now point of view of I'm studying defects in some theory, I can think that I put some operator into n equals 4 super Young-Mills, and I ask myself, what is this going to look like in the other side? And people understood very well, Witten understood in the very beginning that when this delta is very small, order 1, for example, this local operator is going to be some perturbation of the metric, perturbation on top of ADS5 cross S5. When delta is of order n, now this has many more degrees of freedom, and the correct description is going to be some brain on ADS5 cross S5, and this is what we use to describe a lot of the defects that we were talking about this week. And then we can study this regimen of huge operators of conformal dimension that is of order n squared. And for the specific case of a correlation function of two local operators, chiral primary operators in n equals 4 super Young-Mills, this is completely fixed by conformal dimension. The only thing that we care about is delta. Lin, Lunin, and Maldacena in this paper were able to understand that the correct description for this operator is not in terms of these giant gravitons that were these brains, but in terms of some new back-reacted geometry. It is a new back-reacted geometry that is asymptotically ADS5 cross S5. So I know that I am putting something onto n equals 4 super Young-Mills, but I'm still finding n equals 4 super Young-Mills. And but it's a solution that has a non-trivial topology in the interior, and that is why it is going to be one of these examples where you cannot just expand in spherical harmonics and be happy about it to compute the Onsel action. So what I'm going to be calling bubbling geometries are these kind of solutions. There are, like now, many people have worked on a very long list of such that solutions. They are going to be asymptotically ADS5 cross S5, and as I said, they will have non-trivial topology. And in particular, they are all, it's not because they are singular, they are all smooth geometries everywhere in the interior. They don't have horizons, but they have this non-trivial topology. And I will not be talking about this bubbling geometry for local operators, but about the one for surface operators. But just to mention, it both in n equals 4 super Young-Mills, people know what is the gravitational dual of Wilson loops of representations that are order n squared. They are some geometries, boundaries that are dual to some geometries and not just to some like end of the world brain. So there are many examples, and not only in n equals 4 super Young-Mills, but in other theories, like we heard the other day about ABJM. These bubbling geometries are known for many defects. So this question that I am answering today for only one specific case can be asked in many other different examples. Okay, and so the more concrete question that I am trying to answer is how do we do holographic renormalization in these geometries when the method that Skenderis and Taylor gave us doesn't work. And I want to say that there are several papers that talk about this problem, but I only found one paper that tries to work on this problem. It's this paper by Taylor this is in 2006, in which they propose this higher dimensional approach to counterterms. That is the same thing that I am going to explain, in which, for example, they discuss she discusses how to put a counterterm for a continuous distribution of the three branes. and she discusses why this problem is very complicated. And yes, I just want to enumerate some of the reasons why this question is really hard. And they are all related to boundary conditions. I think that something very important is that from the 10-dimensional point of view, the boundary is degenerate. Because when we write, so we write the metric for ADS5 crosses 5. Oh, I think you can you see or no? Okay. And so I have the radial coordinate of my ADS5, and then I have the metric of the 5 sphere. And when I try to go to the boundary, that is when C goes to 0, the 5 sphere shrinks to a point. So the conformal boundary of this 10-dimensional space is some 4-dimensional space. So when you do the usual ADS-CFT, people understand well what is the meaning of the regulated boundary at C equals to epsilon. And indeed, that has been very important to understand what happens when I move epsilon and what does this mean physically. But now when we try to think about this from a 10-dimensional point of view, we have this problem that when I regulate the 10-dimensional action, I have a 9-dimensional boundary. Does my 4-dimensional theory live in a 9-dimensional space? That doesn't seem to make a lot of sense. In general, what are the correct boundary terms to put in this 9-dimensional boundary? We don't know. And also in 9 dimensions, like you can put so many things. Like if you start by just adding powers of the curvature, or like any other contractions in a similar way to the diffeomorphism invariant way of writing counterterms in ADS, you just have a gigantic list of terms. How do we choose? And especially, what is a good physical intuition to why add this counterterm and not this other counterterm? This question I am not going to answer, but I think it would be very important to work on that. And then there is the problem that the Pfefferman-Graham expansion, that is something that is really essential when doing, that is really essential when doing holographic renormalization. It works for asymptotically ADS spaces. So there is this theorem, but there is no analog for this, because this 10-dimensional space is not asymptotically ADS10. So I cannot try to mimic the Pfefferman-Graham procedure in that way. And maybe something else to mention is that in the 10-dimensional and 11-dimensional action don't have, so in 5 dimensions, this is very silly, so I don't need to turn the light on. We have some like cosmological constant term, but in the higher dimensional case, there is no cosmological constant in the action of supergravity. So you can prove that the on-cell supergravity action is going to be a boundary term. So just with the homogeneity of the fields and the action, you can prove this. And then, yes, you just have the question of not only with the metric, with all the other fields of your theory, you have all these boundary terms that you can add, and all these different reasons why you could want to add boundary terms related to, I don't know, gauge invariant. There has been some work on that related to complexity or many other reasons. In general, yes, I don't know. There seems to be a very, very long list of reasons why it is hard. Sorry?
I can add another one. So I work on the t-squared definition, sometimes called TT bar, where you move the bound, deform the boundary so it moves to a finite value of z. As far as I'm aware, people would only ever look at this in this context, a 5-dimensional sense. But really, if you're at finite t, there's these extra dimensions. And so I don't think there's any work that I've seen yet on understanding this as a non-dimensional.
Yes, me neither. I tried to look for something like that, but I didn't find anything. So if anyone has a suggestion to an answer to any of these questions, I would be super happy to hear about it.
Can do a consistent rotation. You know the counter terms 5D. Can't you figure out what should have written in 10D?
There are a few examples of that, and so I've seen a few papers where people mention, oh, if you just take the 10D or 11D axion and you just plug in the vacuum solution, just like that without thinking, you don't really get the correct number, like for example, for the central charge of the theory or for like the free energy. But then they are able to do this like reverse engineering of like, oh, I realized that that I can add this boundary term that corresponds to this in the lower dimensional theory. I think, yes, I tried to do. Maybe it does, but it didn't. Maybe it taught me something, but I didn't learn it. That is possible. I wasn't able to apply it very well. It is true, you will see that the counter term that I will use is the first counter term that anyone would write down. That is a counter term that is just proportional to the boundary of the regulated area. So when I saw that that worked, I just stopped there. But yes, this question of trying to use the lower dimensional ones that are known and trying to use them is something that I am trying to do too. Yes, maybe before I continue, is there any other question? Okay, so the very, very concrete example that I am going to be discussing is the case of one of the defect conformal anomalies of this operator, this half BPS surface operator in n = 4 super Young-Mills. I'm going to compute it from the on-cell 10-dimensional axiom. Okay, so now I will review the definition of this operator and the parameters that appear in this defect. So this is a conformal surface operator. We have this 2-dimensional manifold in R4, and we will be for it to be conformal, for it to be supersymmetric, you cannot pick any manifold. You need to restrict to the plane or the sphere. And you see that the 4-dimensional conformal group is broken, as what we learned yesterday. And in particular, you can study what are the conformal anomalies of this surface operator. So. Yes, all these people worked on this, on deriving why these three coefficients are the parity invariant conformal anomalies. And you see that even though this 2-dimensional surface operator that is conformal, I can understand it as a 2-dimensional conformal field theory, it has a much more rich structure than a 2-dimensional conformal field theory, which only has one conformal anomaly. Here we have these other two conformal anomalies that are related to the way in which the surface is embedded into this. This works for any dimension, but I'm going to focus on d = 4. And so Andy and his collaborator proved that this B, they showed it obeys a C theorem. This is the one I'm going to be focusing on, but these other conformal anomalies are related to the 2-point function of the displacement operator and to the correlation of the bulk stress tensor. So this C2 gives us a definition of conformal dimension of a non-local operator. This is something that can be defined for other operators, and this conformal anomaly, since it's related to the stress tensor, we can use this procedure, we can use this Kaluza-Clarin procedure of Skenderis and Taylor to compute it, and people have done it. So this C2 has been computed using supersymmetric localization. I don't think I will show the result later, but that we did it in our previous paper. And it exactly matches the supergravity action when you use this procedure. But I'm going to be focusing on B, because you see that when you take sigma to be a two-sphere, this thing is going to vanish, this thing is going to vanish, and you can integrate this expression, and you understand that B is something that you can read off the expectation value of the surface defect. So, and we know that, yes, the expectation value of the defect, I can understand it as like the partition function of the theory in this like new vacuum. So in holography, I need to be able to reproduce this from just the pure on-cell action. So again, this doesn't work. And in particular, we are going to see that, okay, and I didn't say, but this R is the radius of the two-sphere, and this R0 is just a scheme-dependent constant. So the constant in front of this is scheme-dependent, but B is scheme-independent. And so we are going to see that that when that should be equal to the supergravity on-cell action in whatever is the gravitational dual to the surface operator, should give us B times log of R, and we will see that this log singularity is going to be a singularity that appears in the volume of some ADS3 that appears in the solution. And yes, and I just want to explain how to do this. But first, I need to say what is exactly this surface operator and what is B. Because in order to do this matching, as I said in the beginning, we need some quantities that we know for all values of the coupling constant, for all values of n. It would be here. I'm not going to. Everything is going to be in the planar limit. I'm not doing any 1/n correction. Everything is planar limit, but for all values of G. So this half BPS surface operator of n equals 4 super young Mills was introduced by Gukov and Witten in 2006, and it depends on a lot of data. It is so you know, or I think everyone knows that the Wilson loop, for example, half BPS Wilson loop of n equals 4 super young Mills only depends on the on a representation of UN, which basically means I have this probe particle in some representation and I move it around. Here I could think that I have this probe string and I am moving it around, and this is how I define this surface operator. But it depends on many continuous parameters, which is very different from the Wilson loop and makes it some observable that is very interesting for this reason. And so it depends in all these continuous parameters that I will explain now, and in this discrete choice, that is a choice of Levy subgroup, which is that the gauge group UN, when you restrict yourself to the surface operator, is going to be broken into this product of smaller UNs. And this, I will only talk about the UN case, but people also discuss other groups. And so this is in the classification that Silvia explained the other day, this is a disorder operator, because I cannot write it as something that I insert into the path integral in terms of the fields of my theory, but it's going to be prescribing this singularity. So alpha is this constant matrix with continuous coefficients, and psi is an angle around the surface. So we are in 4 dimensions, so around the surface I have a 2-dimensional plane. Psi is the angle and r is the radial coordinate, and we see that both the gauge field has a singularity at the location of the defect, and also phi is one of the 3 complex scalar fields of n equals 4 super young Mills, is also going to have this singularity. And alpha, beta, and gamma are going to be matrices that are invariant under this Levy subgroup. And then there is this two-dimensional heat angle that is not going to play any role in my discussion. Okay, so I want to compute this B, and this has been, so this we computed it using supersymmetric localization, and we got this, this result. So in terms of the dimension of the gauge group and the dimension of the Levy subgroup, I have to say this also was computed, it was motivated using holography in a different way that I can mention later, not from the on-cell action, but from a relation between B and this should be C2, and the entanglement entropy in the presence of a defect, and also this was also computed using anomalies. But basically the important thing is that this result is exact, and we want to find this in the on-cell action. And you see that it doesn't depend on any of the continuous parameters that appear in the definition of the surface operator. Okay. And okay. Yes. Yes, I can. Yes. Sorry. Okay. Oh no. Isn't it? It's this one, isn't it? I think now. So, in our previous paper, we used supersymmetric localization to compute several observables involving the surface operator. In particular, this one-point function or two-point function, or what you called one-point function. Then also the correlation function of the surface operator with a Wilson loop that is, so I have the surface and a Wilson loop wrapping around it, and also this expectation value. And the complicated thing is that since this operator is a disorder operator, doing localization is a little bit harder. But what we use is the same localization scheme of the one for the 1/8 BPS Wilson loop of Peston. And the idea is that you start with n equals 4 super Young-Mills on the 4 sphere. And after doing this localization, you go to the Young-Mills, non-supersymmetric to the Young-Mills on a 2 sphere. And you do this by writing this 4 sphere.
I'm curious to understand what is the object that you will put in the path integral corresponding
to the surface operator. Yes. So, so the S4, to do this, you write it as a 3-dimensional solid ball and a circle with some like warp factor, and so you would think that maybe and I think what Pestum mentions in this paper is that the natural thing to do is wrap this surface operator on the sphere, but if you do this, it doesn't work. The supercharge that you use in this localization, if you put the surface operator like that, it is not a supercharge of the surface operator. What you have to do is you have to insert it. It is going to be a 2 sphere, but it's a 2 sphere that you write from this interval that goes from the South Pole to the North Pole and also wraps this circle. So then when you go to 2D Young-Mills, the singular behavior that I showed before is going to correspond to some vortex configuration in the North Pole and the South Pole. And so again, you get 2D Young-Mills, but you need to do this quantization on top of the singular configuration. No, it depends on the parameters of the surface. It doesn't depend on the continuous parameter.
Yes.
So So it depends on the Levy subgroup, but it doesn't depend on this. And we can understand this B as some like central charge that is counting the degrees of freedom. I know there is a reason to know a priori that it cannot depend on continuous parameters, but I don't remember. But all the other observables that we compute, but all the other correlators that we compute do depend on all the continuous parameters. I think there is some anomaly argument that I'm not remembering. Sorry. I will think and tell you later. Yeah. They asked me this in my committee meeting 1 month ago, and I forgot. Sorry, you have an answer?
Match two surface operators with the different parameters.
So no, all these surface operators are different. So all these so they are. I just put the label of the surface because it's too long, but each of these. So this surface operator depends on a choice of Levy subgroup and then 4m real parameters.
But you can surface operator as obtained by sort of deforming the first one by adding some extra. Not adding, by changing smoothly the parameters.
I'm not sure. I know that from the perspective that you and the other talk yesterday of I am adding this deformation to the surface, all these parameters can be understood as you have these exactly marginal operators so this operator preserves 4,4 supersymmetry in 2 dimensions, and you have these operators that you could be adding to this 2-dimensional surface, and these are the coefficients.
You know, because I'm thinking, since the local the matrix model does not depend, it gives you a result which not depends on the parameters. I tend to think that, you know, if you take two different surface operators, because they correspond to different sets of parameters, there is sort of cohomological equivalence, you know, because if the two differ by a Q of something, of course the matrix model will give the same result for B.
But I think for different parameters, they...
You are saying B is the only one and the only anomaly which does not depend on the...
Yes, that's true.
You make those marginal parameters functions of position very slowly, and the anomaly term.
Yes, I think so. I think so.
Coefficients of an Euler density
Cannot.
will be independent of marginal couplings for that.
I see.
Because the Euler density term under conformal transformation changes.
Even better. Okay.
So it's stronger than super.
Yes, this is what I didn't remember. Thank you very much.
Start minus the group that is preserved. Is it proportional to some Goldstone holography? Like, is it some counting some degree of freedom related to the breaking of the UN?
I never thought it as some Goldstone because I don't think like this is not like I don't think it's a spontaneous symmetry breaking. It's just maybe there is another picture of the instead of thinking of this operator like this, you can think of the definition of the surface operator in a different way. That is, you have this 2-dimensional theory that has a quiver description that is like a very complicated quiver, but has UN global symmetry. And you can couple it to the bulk that has UN gauge symmetry. And when you couple them, what you do is gauging this UN global symmetry. So yeah, I say that when you go to the surface, you break it, but I don't think it's like dynamically you have spontaneous symmetry breaking. But it is true that this B, and this is very clear from the holographic description, why it is counting different, like these degrees of freedom. yes, so maybe with the holographic description I can explain, because we will see that depending on if B is order n or order n squared, the same way that I was explaining for like the giant gravitons and the bubbling geometries, we are going to have different description of this operator. So,
however, differing by total derivative is Q exact, because the total B is presumably Q squared. You can interpret it as a Q homological equivalence.
Without superseding.
It's true, even without superseding.
okay, so so these operators, as I said, were introduced by Gukov and Witten in 2006, and in that paper and in this other paper by Drucker, Gomis, Matsuura of 2008, they studied what is the holographic dual to this operator. There was this nice earlier paper in which they studied the defect CFT that lives in the intersection between these two stacks of D3 branes. And when I went to read this paper, I don't know, it's when I learned that people talked about these CFTs this early on. I don't know why, but when I started like my master's and my PhD, I thought that defects and DCFTs and all these things were something from 5 years ago, but clearly I was super wrong because you have been working on this for a long time. But there is this configuration that in the intersection preserves n equals 4,4 super symmetry that is the same as the surface operator. And you see that they intersect along this two-dimensional surface, that is where the defect lives. And now we need to think of taking n to infinity, because this is the branes in which n equals 4 lives, and we will see in which case there is a better description in terms of branes or in terms of geometries. So in the case when n prime is of order 1, the correct description for this system is going to be that of some probe branes on ADS5 x 5 that intersect the boundary along a two-dimensional surface. And in these papers, they study very much the case of one probe brane. And one probe brane corresponds to this breaking, that is breaking the group as little as possible without leaving it all unbroken. And you see that if we use our formula for B, in this case, B is of order n. So we see that that is the brane description of the operator. And so using this brane description, people were able to compute all these correlators that I mentioned in the strong coupling limit, and evaluating the on-cell action of the D3 brane. This was more recently than people, because they evaluated the action in this paper, but the choice, so you have a solution with a certain form in this D3 brane, but in this paper they chose a form that wasn't globally well defined. So it seemed to give that the expectation value of the surface operator was 1. But then in these papers they realized that when you pick a form that is globally well defined everywhere, then you get the correct anomaly, and they get this 6n. And I thought it was very cool that in this recent paper from last year, people were trying to compute the 1/n correction by doing one loop corrections to the probe brane action, but it still seems very hard. I don't think it is well understood. But as I said, I'm only going to care about large n, but I want to do the generic case. And in the general case, we will have many n prime D3 branes, and you will not be able to describe it as, if you have an order n of D3 branes on ADS5 x 5, this is not a good description because the branes are too heavy, and what you will have is this, I draw these bubblings, these back-reacted geometries that are asymptotically ADS5 x S5. And so I'm going to explain what are these geometries, because what I'm going to do at the end is evaluate the type 2B supergravity action in this specific geometry. And we see that all the symmetries of the surface, the way that they found these geometries, again, is not by solving type 2B supergravity equations, which are very hard, but by using the symmetries. The symmetries of the surface operator appear as isometries of this solution, and they preserve the same supersymmetry. And again, they are smooth solutions, and they don't have horizons. So all the problems are not related at all with like singularities of the space-time or anything like that. Okay, and there is a map between all the parameters of the surface operator and the parameters of the solution. And this is the solution. It is a solution that in which the only two fields, it's like the easiest out of all the bubbling geometry solutions. That is why it's the only one that I know how to do, or in which my boundary term has worked so far. Only the metric and the phi form are non-zero. And so we have this ADS3 that is related to the conformal unbroken conformal group on the defect, S3 that is related to the symmetries of the unbroken R symmetry. Then we have this circle that we know that the correct or like a natural metric to think surface operators in 4 dimensions is ADS3 times S1 by doing a conformal map from R4. So all the symmetries are here in this ansatz. And what they show in this paper using using the LLM paper, they saw that all these factors can be written in terms of just one function. And this is one function in this 3-dimensional space. That is a 3-dimensional space where y is always bigger than 0, so it's like half space. And this function obeys some differential equation and some boundary conditions. And the boundary condition is that when you go to this 2-dimensional plane, the 3-sphere shrinks to 0. And for people that is familiar with the LLM geometries for the local operators, but maybe are not familiar with this one, you can see that y is the product of the radius of the ADS3 and the S3. So in y equals to 0, one of these two has to be 0, and the radius of ADS3 cannot be 0 because it's a non-compact space. So this is the only boundary condition. In the LLM case, what they had is that the solution was specified by some droplets where where one sphere shrinks to 0 in some parts, and this ADS is analytic continuation of S3, and you have this difference of which 3 spheres shrinks to 0, but it's much easier here. And that is the reason why with this differential equation, to which you have to add some sources, like point-like sources, so that it has a non-trivial solution, and you see m sources. So this is the first map between the parameters of the surface operator and the geometry. You can solve this equation exactly. Oh no, I didn't. Okay, I didn't write the solution, but you can write it exactly as a sum. Like the solution is a superposition of like some rational function with some square roots. But you can write it explicitly, which is not true. So these other bubbling geometries that I mentioned, for local operators, for Wilson loops, all those ones, you cannot like solve analytically for all the cases. That's why this one is easier. And you see the non-trivial topology because this function C goes to infinity at the location of all these point-like particles. So this warp factor goes to 0, and I can build some topological 5-sphere by joining a 3-sphere that shrinks to a point and a circle that shrinks to a point. So all these pink solid lines represent non-trivial 5 spheres of my geometry. And it is useful to see how we can see the vacuum in these coordinates. It corresponds to the case in which I only have one point particle. that is at that I can put it here at the origin because I have translational symmetry. And when I use this change of coordinates from this LLM paper, I can see that the very complicated metric from before with this pretty ugly C that I didn't write, but I told you we know what it is, becomes ADS5 cross S5 in a metric that maybe is not so familiar what we normally use, but is very familiar when thinking about surface operators, because it's an ADS3 times S1 slicing of ADS5, and then a 5-sphere slicing of a circle and a 3-sphere. And so what we want to do now is that is the thing that I will explain this now, because I did this change of coordinate that is, yes, it's like very, like it's an involved change of coordinates. So here, from this description, it is not clear what is the asymptotics. The asymptotics are ADS5 cross S5, I will show now, but most of the problem of this evaluating the 10D on cell action is how do we find these asymptotics, what is the correct radial coordinate, what is the correct cutoff for the radial coordinate. This is what I'm going to be discussing. Yes, I will explain how, but it's like it's a little bit complicated. It's not immediate. It's not just fixing y equals to 1 over epsilon, for example. That doesn't work. C doesn't go. Sorry. No. This is not 0. This is 1/2. Thank you. Very well. Yes. No. This is not 0. Absolutely, yes, this is wrong. Sorry, the boundary condition is C equals 1/2. And in the LLM case, it changes from C equals 1/2 to C equals minus 1/2. I'm sorry. Yeah.
You mentioned that these geometries are related with analytical continuation with LLM. So this means that you have the same structure like 1/2 BPS, blah, blah, blah.
They are 1/2 BPS too, but so it's a double analytic continuation. In the LLM geometries, you have S3, S3, and R, because this is the time direction. And here, the time direction becomes a circle. And one of the 3 spheres becomes this ADS3. So the solution itself looks very different. In this case, you also have all these 2-dimensional disks that I'm not going to explain it, but in order to map it to the parameter of the surface operators, these are non-trivial disks because I have the non-contractible circle in the boundary, but in the interior it is contractible, and the integral of the B field, like the two forms of type 2B supergravity along these cycles are going to be non-trivial, and they are going to map to those operators. So even though they are analytic continuation, then the solutions are very different. You see it in all these 5 spheres. These 5 spheres, you cannot shrink them to a point. Normally, in ADS5 times S5, we only have one 5 sphere, the S5. And here, what I'm going to show is that asymptotically, you have some S5. So there is going to be a definition of what Yolanda asked. There is going to be a definition of a radial coordinate. And at infinity, I will find that 5 sphere. But in the interior of the space, so where the location of all these point-like particles that are not real particles, it's just, I have these 5 spheres. And in all the different bubbling geometries, you have similar phenomena in which you have, for other defects, you have maybe non-trivial 2 spheres and 4 spheres that are like supported by the flux. So the idea is that, see, maybe this is useful. The location of all these particles in the plane is related to the location of the n prime D3 branes. And the height of the particle is related to the number of D3 branes at that point. So it is as if these D3 branes backreacted, and now these non-trivial cycles are supported by the flux. In the sense of, if now I do, I think I didn't write it, but if I take F5, this one here, C1 and C2 have some horrible expression that I will show later, but if I integrate F5 in any of these 5 spheres, I'm going to find the number of D3 branes. So this N corresponding to the Levy subgroup that represents the number of D3 branes that was there. And I have to say that from the brain perspective, so the probe brain case is well understood, but it is not understood how from a generic brain intersection derive the generic Wilson loop, for the generic surface operators. For the Wilson loop, for example, that is understood. Like if I take a Wilson loop in the k power of the like k antisymmetric power or symmetric power, people know how to engineer it with like D3 branes and D5 branes and how to derive the Wilson loop. For this case, you cannot do this. Okay. So, or maybe because I will not explain more things about the geometry, if anyone has any other questions about the geometry. Okay, so now I want to evaluate the type 2B Onsel action on this solution, and only the metric and the 5 form are non-zero. So this is the action. We have the Gibbons-Hawking-York term, and then we have the counter terms that we know they should be there, but they are completely unknown. And then this is problematic because the 5 form is self-dual. So I will just use the, like many people discussed, how to, it's a 5 form that is self-dual, so it would evaluate to 0. But what I'm going to do is use this prescription that has been discussed, like what it means physically, of splitting F into an electric part, that is going to be this part here, that has legs on the ADS on the ADS direction, and a magnetic part, such that star of F electric is F magnetic, and we are going to evaluate this on this action. And I have to say that this was done in 2015, and I will show you now the result, and you will see why it cannot be correct. It cannot be giving us the correct result. So using this expression and the differential equation that C satisfies and all this, you can see that this term can be written in terms of these 3 things: an integral of y times the C function, then a total derivative, where u is this thing that I wrote here, and then this is something, some other term, but that vanishes using the equations. And so now you have the question of how to evaluate this, because so we have these 3 terms, where I1 and I2 come from F squared, and then I have the Gibbons-Hawking term. And remember that if I want to reproduce the exact result that I gave you from quantum field theory, what I need to find is log delta, log lambda, that is going to come from the divergence of this ADS3, and then conformal anomaly divided by 3. That's all. I don't want anything extra. And so here I have C. So this is C. It's this superposition of M terms that look like this, and you imagine that if you just plug that into here, that is going to be an integral that you cannot do. So, so the procedure to do this, to solve all these integrals, is do what Yolanda was saying. We want to expand this function for some large rho. Especially, we see that 2 of these integrals are a boundary term. So only contributions for the boundary are going to be relevant. But again, 9-dimensional boundary term. And then this one can be computed, but I will not explain the details. I can give you the reference for this integral. And so we need to define this cutoff. And I want to say that in general, defining the Pfefferman-Graham coordinate in these cases, it is not well understood. And I think even for the case in which you don't look at the 10-dimensional space, but you just try to do Pfefferman-Graham for defects. So for ADS written with some smaller ADS slicings, I think maybe this is not completely understood yet. But I'm going to use a prescription that is used in all these papers, and that gives the correct answer when you compute RT formulas in this 10-dimensional metric, and I will explain what the prescription is. So the idea is that we want to expand around the vacuum. So I have the vacuum solution, and then I have a perturbation. And this, I am going to write it as, and this delta G, delta F, I'm going to write it after doing this change of coordinates that we learned from Lin, Lunin, Maldacena. I'm going to write them as power series in 1 over rho. And when I do this, I see that the metric has this form. So all the warp factors, I have expanded them in rho, and yes, and I can write all these functions in terms of the coefficients in the expansion of C and V, and it's going to be useful to write everything in terms of these momentums that are this combination of the position of the particles, because I didn't explain, but the position of the particles encode all the parameters of the surface operator, and in particular see that M200 is going to be L to the 4, and M400 is going to be the dimension of the Levy subgroup. So it's something that we are after. And then when B and C are non-zero, the parameters that encode the positions of the brane, so the continuous parameters, beta and gamma, will appear. And okay, so we expand using these momentums at large rho, and we are going to pick a gauge for this one form V that I didn't explain so much before, such that the rho component is 0. This we can do it because, okay, I think that. So V obeys this equation. So V is defined up to a total derivative. So I can use this gauge transformation to bring it to this gauge in which V rho is 0. And I do this so that rho doesn't have cross terms with any of the other coordinates, in such a way that this is a good candidate for Pfefferman-Graham coordinate. Okay, but the Pfefferman-Graham coordinate that we will define is not this one, because you see that even though it doesn't mix with the others, we have this f of rho here that is non-zero, and we don't want that. What we want is for the Pfefferman-Graham coordinate to be some ADS5 radial coordinate. So I want some U such that this term in the metric is of this form. And oh, I didn't put the reference here, but in these papers, like these papers of Andy has a lot of work explaining why this is a reasonable cutoff, because in this context we have the problem that we can go to the boundary both in the rho coordinate and in the ADS3 coordinate, and this depends on if you go to the coordinate away from the defect or on the defect. So here we want to fix this ADS5 Pfefferman-Graham coordinate, and you do this by doing some change of coordinates asymptotically in rho and then inverting it. And the important thing is that then this new cutoff that is going to be U equal to epsilon is going, when I go back to my rho coordinates, is going to give me a cutoff that depends on the angular coordinates. So I have this cutoff surface that is like a wiggly surface. And something that I wanted to mention is that maybe you would think that you can just put rho equal to epsilon and try to see if things work. And the answer is that many of the calculations that were done before this don't work. The on-selection also doesn't give you the correct answer. So it seems that there is some evidence for this prescription of the cutoff.
Just a smooth cutoff, just a smooth like hemisphere. The picture, previous slide.
For the vacuum? Yes, for the vacuum it would just be, for the vacuum it would be, it wouldn't depend on the angular coordinates, that's true. For the vacuum it would be, but it wouldn't be just 1 over epsilon, but I think it's something like 1 over epsilon plus some number over epsilon times epsilon, or something like this. Does this make sense? So it's not just 1 over epsilon. Even when you substitute, so you can take the, you were going to say something?
In the picture.
No, in the picture it looks the same. Like it looks like a hemisphere, but I'm saying that the dependence on epsilon is not, the dependence on epsilon is not just 1 over epsilon. But the dependence on the angular coordinates, yes, it's, it would be just a nice hemisphere. No, in their paper they were cutting like this, because you need to cut like this in order to get the correct entanglement entropy. But and indeed so this result is from their paper. They compute what I called I1, I2, I3, which is f squared and the Gibbons-Hawking term with this cutoff, and what they find is this. This is from their paper, but this, what I'm trying to say now is that this is not the correct answer, because you need to add something else, because you cannot just like evaluate the action and not do anything else. Like it happens in like lower dimensional holography. You cannot just evaluate the action and take the finite term and and take the finite term. But the counter terms are physical. You need to add these counter terms to get the correct physical answer. Yes, sorry. I think there are some field theory calculations. I'm trying to think, maybe for the surface operator this is not true. Or maybe you can. Yes, that's what. So for the, I know for the Wilson loop, for example, you can do the same cutoff. And for the Wilson loop, it is known what is, from field theory, there is this paper, Lukowicz-Maldacena, in which they compute the entanglement entropy, and you can match it with the holographic result if you use this special cutoff. In this, for the surface operator, the reason why you know it must be correct is because there is this relationship that I mentioned before between the entanglement entropy and these two conformal anomalies, and these two are known in the field theory. And in order to reproduce this, you need to use this cutoff. So indeed, this was the way that people computed B holographically before there were exact results, or in which people conjectured B holographically before there were exact results from the field theory. Okay, so here I want to point out that so this is the on-cell action, and there is this term, and it is written in terms of these momenta, and you see that it depends on the continuous parameters. So we know that cannot be true because of the argument that they gave us, and even after doing, like, you do vacuum subtraction and you get this, and it is not what we want. So what I did is try to start with the simplest counter term that is proportional to the area of the boundary, and this number I I put it there and then I fixed it. And when you add this counter term, things work. This very simple counter term cancels this horrible thing, and after vacuum subtraction, to cancel these power law divergences, you get the correct answer. And I want to say that, yes, the cancellation is not like trivial. This is this I1, this is this I2, and they cancel a lot of terms, and then you get this calligraphic F, and for some reason that is the same as this thing that appears when you compute the area of the regulated boundary. I would like to understand better why this is the case, but for now I don't have a very good explanation, more than it just works. But for sure this is not satisfactory enough. I really want to understand better why it works. And I just have some conclusions. That is that, so for this very specific case, we were able to reproduce this, and I want to insist that there is no method to compute this 10-dimensional on-cell action that I know. If anyone, I'm happy to be wrong. And that this is a very concrete and simple example of this general phenomena, but that this has to be true for many other physical observables. There have to be all these physical observables of the 10-dimensional or 11-dimensional theory that we don't know how to compute. And if we want to prove the ADS-CFT correspondence, at least in this case that we think, I don't know, n equals 4, all the supersymmetry, we think this is maybe really true, we need to understand this problem of what to do with all these solutions. And I would really like to have a physical reason for why this counter term works. It's true that since I'm looking at this conformal anomaly, which is scheme independent, it's possible that in general, when I try to do this, I would have to add many more counter terms, but that they don't matter in this case. But yes, I really don't understand why. And then I am working on how to do this for other examples of other bubbling geometries that I mentioned, in which people have computed. The problem is that it's very hard to have examples like this B, in which from the gauge theory side, you know the answer for at strong coupling, and it is an observable like this that is like scheme independent. There are other operators with conformal anomalies that can also be studied like this, but I don't have so much progress, but I'm happy to discuss with anyone later. And yes, it would be, recently I listened to this talk by Jerome Gondlet on using equivariant localization for supergravity. And they have this and his collaborators, they have this beautiful technique to try to evaluate the on-cell action without using the on-cell action. But I think they only know how to do it up to dimension 7. It would be really good, if we could do something like that for the 10-dimensional action, that would be great. And yes, maybe it works, but I don't know how to do it, and I think they also don't know how to do it in 10 dimensions. And thank you. Oh, this is wrong. That is 1 over epsilon. That is, yes. Sorry. Yeah, that's true.
Did you check those?
This was Andy's when I talked to Andy a couple months ago, he suggested to me thinking about exactly this thing. So yes, like adding linear in the curvature and quadratic. And I checked. I checked that with these terms, I can cancel the divergences for the vacuum, but I didn't do the integral for the for the generic bubbling solution. Because in this time, I've been, like, I really tried very hard to work out these other examples that I was mentioning, but they, so yes, but I should do this.
One's positive, one's negative, could that term just vanish in your geometry?
Yes, this term vanishes, but this one doesn't vanish, I think. Yeah. I
It's good. It was some sort of careful choice of both the singularities and the cutoff that led to a simple conclusion. So counter terms and if you were to use a different cutoff description with your singularities
Yes, that I didn't try. I only tried just using the naive prescription, but starting with higher order, I didn't try. I don't know if I can give you an answer right now, but I for sure can try to understand what happens in that case.
Suppose I want to believe in a 9-dimensional holographic dual that lives on the boundary of 10-dimensional string theory. I just cut it off at some finite place, and there's a dual theory that lives in 9 dimensions. Have I learned anything about this theory? Like, what can you tell me about it? Tell me something about China. Can it be phrased in the language of
Yeah, that is what I think conceptually I don't understand, and I don't know if it is the correct approach, like to try to think that I have this theory living in the 9-dimensional regulated boundary. My motivation is just that there are these observables that you cannot study with the usual tools, and that we shouldn't ignore them. Maybe there is another, like, I'm not saying this is the correct prescription. Maybe the correct prescription even for this observable is something else. And maybe there is a way to do something like Kaluza-Klein holography of Skenderis and Taylor and compute this observable from 5 dimensions in some smart way. That is possible, and I would be very happy to know about it. But I'm just trying to point out that this question. But I would like to know the answer to that.
Yeah, so it would have to be evaluated on a particular background that has this S5 and it has this flux. Its behavior might be different than if you just did it in like 10
Indeed, in this case, the boundary, so even if I just take the 4-dimensional boundary, the boundary is ADS 3 times S1, it's not R4. So even these bubbling geometries, I'm pretty sure that there is no solution that is like this with this non-trivial topology, but for which the boundary is R4. So it is possible that even in this case, I am looking at n equals 4 super Young mills in a different geometry. Okay.
That was my question though, was so that the vacuum case worked out
No, but I will. So I was looking at in the 6-dimensional and 2,0 theory, you have a Wilson surface, and this B anomaly is also known, not with localization, but with some anomaly. It is written in terms of the representation of the Wilson loop, and the bubbling geometry is known. And I try to do the same, but things don't. As I said, that geometry is much harder, so this is really the easiest one. And there are some problems. That is that, okay, as I said, this you have this non-trivial topology, so your sorry. So when you write, so normally what people, and people have tried to do this. So in several papers using bubbling geometries, people have like evaluated the axion and tried to like predict something from the field theory, but the results don't match. And what you do is you write the type 2b axion or the 11D axion as a total derivative, and then you don't use F5. That, as I said, this solution is completely smooth, no singularities, is perfectly well defined. You would use the potential, and the potential now is not globally. It cannot be globally well defined because of all these non-trivial cycles. So there is the problem that you need to choose a correct gauge in each, like you want to break your manifold into patches and put the correct gauge, and then some integrals that are very big and look very important when you choose gauge so that things are when you choose a gauge so that the potential is well behaved, then those integrals vanish, but then it is not clear if you want to add, now you have, for example, this like C wedge F term in 11D supergravity, and you have a boundary. This term is not gauge invariant. Is the correct prescription to add a boundary term so that it is gauge invariant? That is also not clear because you will just kill this term. What is the correct prescription? Yes, I tried to. I don't have. I was working on this, but I don't have something very smart to say.
In 11D, equivalent localization, at least a bit. Like there are some papers like gate or validating in supergravity equal 11 to compute dimensional dimensions, but it doesn't work at the moment.
Oh, I don't know. I didn't know. I think I asked, is that Jerome was in perimeter, and I asked him, and he told me no, but maybe.
Not for this observer.
Yeah. Okay, I will check. I'm not. I just know that this thing exists, like, and I heard, like, listen to a talk, but I absolutely don't know how it works very well. So, but thank you for the suggestion.